In this video, we are going to talk about the entropy change for a reversible and an irreversible process. Okay, we try to define what is irreversible process, reversible process in the previous videos, and we also know what do you mean by irreversible process. All the natural processes are referred to as the irreversible processes. Reversible processes are ideal processes which we usually take into consideration when deriving equations in thermodynamics. Okay. So in this video, we are trying to calculate the entropy change for both these reversible and irreversible processes. Okay. Now, this we are going to, for calculating this entropy change, we are going to take two different types of conditions or two different types of system. First system is the isolated system. Second system is one in which we are only considering the system without taking into consideration the surrounding. In these two aspects, we are going to calculate the change in entropy for both the reversible and irreversible process. So let us first look at the isolated system. Now, when we try to define the first one, I introduced to you about the isolated system. We can, if we take system and surrounding together, we can consider them together as an isolated system. Okay. So with that thing in mind, let us look at first the reversible process. Okay. Now, for calculating that, consider Q reversible, that is the heat absorbed. Okay, Q reversible is heat. Okay, so heat absorbed by a system from the surrounding at isothermal condition. Okay, for this, for calculating that, we are considering a system which is absorbing heat, and that heat is Q reversible from the surrounding, and the condition is isothermal condition. Okay. Now, since we are considering a reversible process, we can use this particular equation that we studied in the previous video. That is delta S system is equal Q reversible divided by T. Okay. When we talk about Q delta S system, it would be Q reversible upon T if T is the temperature. Now, if you calculate the change in entropy in the surrounding, it would be delta S surrounding equals minus Q reversible divided by T. Because why minus? Because the heat Q reversible has been absorbed by the system from the surrounding. So for the surrounding, it is heat released. So when it is heat released, it should be having a negative according to sign convention. So therefore, delta S surrounding should be minus Q reversible divided by T. Okay. Now, if we calculate the total, that is system plus surrounding, which is the one that we are trying to understand. So that means delta S universe or delta S isolated would be simply delta S system plus delta S surrounding. So when we add them, these two quantities are same. So they will cancel out, and it will give you a zero value. So that means for our isolated system, the change in entropy is zero, or that means the entropy remains constant for a isolated system. Okay, so that is first important thing that you should keep in mind. Okay, now let us calculate the same for the reversible process. If you look at the reversible process, same system plus surrounding we are considering, because here we are talking about isolated system, so we have to consider system and surrounding together. Okay, so because they are we are trying to consider an isothermal reversible process, therefore the system and the surrounding, they are at two different temperatures. Okay, So suppose your system is at a higher temperature, TH, and your surrounding is at a lower temperature, TC. Okay, and so we know that heat will be transferred from a hotter body to a colder body. Since this system is at a higher temperature, the heat transfer will happen from the system to the surrounding. Okay, so assuming that the uh, heat that is transferred is Q reversible, that means the transfer of heat that is happening in a reversible manner. Though this process is irreversible, okay, we are assuming that the heat transfer that is happening, this process is happening slowly, that it could be considered as a reversible process. Okay, only we are talking it because only then we can apply this particular mathematical form of the second law of thermodynamics. So therefore, we need to assume that heat transfer is happening reversibly from the system to the surrounding, though because they are irreversible process, we are considering a spontaneous or a natural process where the system and surrounding are at two different temperatures. So this itself is a natural process because they are both at two different temperatures. So it's a natural process and therefore irreversible process. But only thing that we are considering here is that the heat that is transferred from a system to surrounding is happening so slowly that it can be approximated to a reversible transfer. Okay, if we assume that condition, then we can apply the mathematical form of the second law of thermodynamics. In that case, delta S system would be simply because it is released. Now, system it is at a higher temperature, therefore it will release heat. So therefore it would be negative. Okay, so negative Q reversible divided by temperature of the system, that is TH. Similarly, for the surrounding, it would be Q reversible upon TC. Now, delta S isolated or delta S universe would be simply delta S system plus delta S surrounding. So when we put these relations here, we get this particular equation, and then we take Q reversible out. So it would be 1 by Tc minus 1 by Th. Okay. Now, this particular quantity, okay, this particular quantity would be a positive quantity. Why it would be positive quantity? Because Tc is smaller than Th. Therefore, this quantity would be larger than this quantity, and therefore, whatever value you get would be a positive value. And therefore, what happens? This delta S universe should be always greater than 0. Okay, so what does this say? For a irreversible process or for a natural process, the entropy increases. The entropy increases. Okay, so now you just compare both. For a reversible process or an equilibrium process, what happens? The change in entropy for a reversible process or an equilibrium process is 0 or is constant or is conserved. Okay. However, for an irreversible process or a natural process, the change in entropy is always increases. Okay. Now let us look into the second type of system where we are considering system only without taking into consideration the surrounding. Okay. So here we use the first law of thermodynamics. Okay. So from the first law of thermodynamics, we know that what Q, delta Q is equal to du plus dTV. Those who do not understand this equation can refer to the first law of thermodynamics where we talk about this particular equation. So this is dQ is equal to du plus dTV. Okay. Now for a reversible process, we know from the second law of thermodynamics, delta Q reversible is equal to T delta S. Now, if we put this particular relationship here, because since we are talking about Q reversible, So this expression would be delta Q reversible equals du plus dV. Okay, and so if we put the dq reversible here, it would be simply T delta S, because this is dq reversible, which we'll substitute here. Okay, so we will get TdS equal to du plus dV. And now, if we consider a hypothetical situation where you have the internal energy and volume constant, in that case, these terms would come out to be 0. And therefore, this equation 3 will reduce to ds. Only ds term would be left. So ds, these subscript imply that internal energy and volume are constant. So these would be equal to 0. That means for a reversible process, your change in entropy would be equal to 0, provided there is no change in internal energy as well as volume. For finite changes, you can replace this differential symbol with the capital delta, and so we have capital delta S UV equals 0. Now, if we do the same for the irreversible process, now here one step I can write here. The same equation we are going to use. So we are talking about irreversible process. So therefore, delta Q irreversible, okay, would be equal to du plus P dV. Okay, this would be the case when it is irreversible process. Okay, now we know that always the reversible change in heat would be always greater than the irreversible change in heat. Okay, so therefore now we know that Q reversible is T delta S. Okay, so therefore we can write that Q reversible is nothing but T delta S, so that we wrote here, and Q reversible is U plus P delta V that we have written here. Okay, so again at constant temperature, constant internal energy and volume, these terms would cancel out to 0. Okay, therefore it now becomes ds at constant internal energy and volume would be greater than 0. Okay, because this term is 0, so if you bring t, it is already 0. Okay, so if you talk about finite changes, it would be again delta S UV, constant internal energy and volume, would be greater than 0. Here again, almost the same relationship you find here, that when you are talking about a reversible condition or an equilibrium condition, the entropy changes 0. And when you are talking about irreversible change, the entropy change here is entropy changes always increasing. Okay, so this two things you can convert it into a statement. For a reversible process, the entropy change of the universe is 0 or constant, or even you can write is conserved. Okay, so in that case, that is one statement. So that is one statement of a second law of thermodynamics. Another statement you can write is, for an irreversible process, the entropy change of the universe increases. Okay, you can combine these two statements, and that would be the statement for the second law of thermodynamics. So what does second law of thermodynamics say? It says that when you are talking about a reversible process or an equilibrium process, the entropy change would be constant. There would be no entropy change, and it would be conserved. However, when you talk about a kind of irreversible process, then the entropy change of the universe will keep increasing. Okay, so that is the statement for the second law of thermodynamics. Now, just to discuss slightly about some of the important things, like if you talk about entropy criteria for spontaneity, like how entropy could be used to decide the spontaneity, now you understood. that for a spontaneous reaction, whenever we are talking about, it is referring to irreversible process. So for a spontaneous process, we know the entropy criteria should be that it should always keep increasing. That means it should be greater than zero. Okay. So entropy criteria for spontaneity is that the delta S universe, okay, or delta S isolated should be greater than zero. So that is the entropy criteria for spontaneity of a natural process. Now, what is this physical significance of entropy? Physical significance of entropy is almost the same as we just now. Physical significance means what is the actual implication of an entropy. So physical significance, when it comes to, we are talking about natural process. So natural process, the physical significance of entropy is that the natural processes, the entropy should be always increasing. Or that means the total change in the delta S, total change in the entropy of the universe should be greater than zero. So that is the physical significance of our entropy. That means the entropy of the universe will keep increasing. That is what the physical significance of the entropy says. And entropy criteria for equilibrium. Equilibrium means it's for the reversible process. So entropy criteria for an equilibrium or a reversible process is that there is no change in the entropy, or rather it is zero, and its value is constant or it's conserved. Okay. So these three questions can be asked interchangeably. There, basically, you have to use all these inferences that we got from the reversible and the irreversible process and explain each of them. Okay, so that's all in this video. Thank you. Have a nice day.